Welcome to the teleoperation of the Baxter robot using the Phantom Omni. This project was created by Chen, Garrison, Johnston, Sutton of Team 15 Omnics. The goal of this project was to use a Phantom Omni to teleoperate a Rethink Robotics Baxter robot with force feedback in order to allow users more feedback in their operation tasks. Cross-communication between multiple platforms was one of the most difficult aspects of this project. However, using Robot Raconteur, defining our own functions, as well as ROS, we were able to communicate between the two systems. In order to control the Baxter robot with the Phantom Omni, we first had to calculate the forward kinematics of the Phantom Omni robot. We then built a simulating file that gave us the properties needed to control the Phantom Omni using MATLAB. In MATLAB, we wrote a script that would take the forward kinematics of the Omni and output a delta position. This delta position was sent to the Baxter robot through a ROS node and interpreted in that system with inverse kinematics so that the Baxter robot could teleoperate. Here's a video describing the procedure. As you can see here, the Phantom Omni is moving, and in MATLAB on the right, which is running on a Windows 7 computer, is calculating the delta position for the Baxter robot. On the Baxter side, which is running on Ubuntu, it is taking those delta positions, calculating the forward kinematics and the current position of the Baxter robot, calculating the inverse kinematics to find the joint angles necessary for the next position, and combining those two to allow teleoperation.
The Baxter robot was simulated using Gazebo running on ROS Indigo. This simulator was developed by Rethink Robotics and is part of the Baxter software development kit. This software development kit, along with the Baxter Robot Raconteur bridge, was used to create a service that allowed MATLAB to send the Baxter the change in workspace positions from the Phantom Omni, and then those change in workspace positions were translated to the corresponding joint angles using the software development kit's inverse kinematics service. The series elastic actuators used in the Baxter allow for a wrench applied to the end effector to be proprioceptively estimated. This can be computed using the Jacobian transpose method solved for the applied wrench using the Moore-Penrose pseudo-inverse. This method works well for when the robot is away from singularities. However, when it is close to a singularity, the estimate becomes poor. To minimize these errors, the singular value decomposition of the Jacobian transpose can be computed, and then a singularity robust pseudo-inverse can be created by inverting the sigma matrix. This allows for better estimates of the applied wrench to be made. This is a video of the Baxter interacting with a simulated environment and sending the wrench it feels from the interactions to the Phantom Omni.